Hello, I'm a little floating head. Uh, sorry. Okay, being serious. Um, so as you guys know, obviously I'm not here today. Um, as promised, I made this video so that you can hear me walk through the notes rather than just reading them. If you'd like, you can definitely just click through the slides that are posted on Google Classroom. Um, you should be able to answer all of the questions from that. If you want to kind of hear a little explanation or have it read to you, that is the purpose of this recording. So let's get started. So obviously, I'm not here. You are going to work through the section of this PowerPoint that is titled DA at Wedding Day 1 Work. Um, as I said in class, your work will be graded specifically on accuracy. I'm referring to the um, reflection that is on Google Classroom with today's date on it. Once again, your answers can only be the ones that come from these slides. They cannot come from ChatGPT, Google AI, or anyone else that is not DA. Okay, so even though I'm gone, I did want to make sure that you guys have a warm up, so you're still filling out your weekly point sheets. Formation of ions notes is going to be the title of the notes as you'll find them on Google Classroom. Today you will be also customizing your periodic tables. If you don't have yours, there are some up at the front in the bin that says handout pickup. Your periodic tables will also be graded, and so you cannot choose not to do this unless you want to receive a 0, which that is your choice. And like I said, you're going to end with the reflection. So here's your warm-up. Feel free to pause it. The answers will be spoken about when I come back. So make sure you have something written down, and then we'll talk about what the answers to these are. You should be able to answer them now, and if not, by the end of this video. So I'm going to start going through the notes. Once again, you should have the formation of ions notes open as you are listening to this. I would do it where I have the two windows open. One of them is me talking. One of them is the notes, so you can type in as I'm going through. Feel free to pause the video at any point to make sure you're getting everything. Rewind it to hear something again. I'll do a little pause to give you time to pause the video, but I'm going to move through it kind of at a normal pace, or I guess a pace as if you're answering everything right away. Okay, so take a second, get your notes open, and then we will continue. So at the top of your notes, you should see these same four intro questions. I know the fourth one is covered up, but you can see it on your page. We're going to go through and we are going to answer these questions. So let's say we have this Bohr model. Okay, for number one, I want to know, how would you identify the element that this is, right? What element on the periodic table did I just draw? Okay, hopefully you know that it's based on the number of protons, or that number that's in the middle, right? We know this is the number of protons because protons are positive and there's a plus right there, right? And so the only element that has one proton is hydrogen. Okay, so for number two, let's say we wanted to change the charge of this atom. Right now, this atom has a charge of 0, right? There's the same number of protons and electrons. There's one proton in the middle, one electron that's drawn, okay? So what would we do to this to change the charge of this hydrogen? Hopefully, you remember that we can't change the number of protons in the middle because that's going to change the element. And so instead, we're going to change the number of electrons, right? We're going to add dots. We're going to remove dots in order to affect that charge. So let's get a little bit more specific. How would we give this atom a charge of 1 minus? What would we have to do? In order to give this a charge of 1 minus, we would have to add 1 electron, right? Each electron is negatively charged. And so for every electron that you add, that thing gets more negative, right? It's like a friend group. The more negative people that are around you, the more negative you start to feel. Okay? How negative an atom is based on how many electrons were added. If it was 2 minus, you would add 2 electrons. If it was 3 minus, you add 3 electrons. Okay? And so thinking of the opposite direction now, if we wanted to give this atom a charge of 2 plus, right, and it wouldn't necessarily work for this one, but for every other element, you would remove 2 electrons, right? If you want to make your friend group more positive, you're going to remove those negative people, those people that is bringing everyone down, and therefore everyone else is going to feel a lot happier, right? As you take electrons away, that atom becomes more positive, okay? So take a second to get these answers written down in or typed into your notes. Feel free to print the notes if that works better for you. Just make sure you hole punch it and put it into your binder. And then when you have that, you can continue with me. So let's talk about the explanation, or I guess the background to the explanation I'm going to give a little bit later. So we're talking about ions, and right, the only reason why ions and reactions happen is so that elements become more stable. Okay. By themselves, elements are very erratic, besides a couple, and they need to be paired up with someone else in order to be in control, you can say, to be stable. An atom becomes stable when that outer layer is full. So that last ring on the Bohr model, when it's completely filled, then it's going to be a stable atom. Okay, and we're going to talk about the different ways in which that's going to happen. Okay, so if an atom has only one energy level, so let's say we have this, right? We have 10 protons, so what element is this? Neon. So let's say we have neon. How many electrons would we need to fill this first energy level? How many can go in the first ring? Hopefully, you know that the answer is 2, right? 2 electrons can go in the first ring, okay? But we know that in order to make a neutral atom, we need to have the same number of protons and electrons. And so we're going to need to fill in another energy level. So let's say an atom has 2 energy levels. All right. How many electrons would we need to fill that second energy level? And so hopefully you remember the number, but I'm also going to show you the placement. The answer is 8. Right? You can fit 8 electrons, 2 at the top, 2 at the right, 2 at the bottom, 2 at the left. And that adds up to 8 electrons. And so this is a neon Bohr model where both the first and second energy levels are full. Okay. So let's talk about why we're talking about how many electrons can fit on each of these rings. So nitrogen naturally has 7 electrons because it has 7 protons, right? Every atom on its own is going to be stable. Or sorry, not stable, is going to be neutral, meaning there's the same number of protons as there are electrons. Nitrogen needs 2 energy levels, 2 energy shells, 2 energy rings in order to hold all 7 of its electrons. We need 2 on the first ring and 5 on the second ring. Okay. The valence, or the outer layer, shell, ring, is the one that's furthest away from the nucleus, so the one that has the red dots on it. Right? Those are the electrons on the ring furthest from the center. Right now, this nitrogen is not stable because there are only 5 electrons instead of the 8, right? We just said in order for an atom to be stable, it needs a full outer layer. Because this atom's outer layer is the second ring, in order for it to be full, it would need 8 electrons, but right now it only has 5. And so in order for nitrogen to be stable, it would need to gain 3 electrons, right? Previously had 5. In order to get 8, we needed to fill in 3 spaces. And so now the outer ring is full. You can think of it like every electron needs a partner in order for everyone to be happy, right? The ones on the first ring, they have each other, right? Essentially, like there's no one else for them to share, so they can be each other's partner. Sometimes you can draw them side by side just to kind of make that seem more consistent throughout. I don't do it, but it's not wrong either way. Now there are more electrons. There are 10. Then there are protons. We still have 7 in the middle. And so this nitrogen is going to have a charge. The charge is going to be 3 minus because there are 3 more electrons, negative charges, negative people, than there are protons, positive charges, positive people, right? The more negative people you have around, the more negative you feel. The more negative particles there are, electrons, the more negative that atom is. And once again, to find the charge, we always take the number of protons, 7, and subtract it from the number of electrons, 10, and that will give you negative 3. So let's look at another example. This lithium has 3 protons, and so naturally it's going to have 3 electrons. Once again, they have to start off balanced. It also, just like the nitrogen, does not have a full valence energy level. Okay, there's only 1 electron on that second ring instead of 8. And so this means that the lithium is unstable. So naturally, every atom is going to be unstable for the most part. So just like with the nitrogen, let's add on the remaining dots, right? So this is what lithium would look like if we filled its valence energy level, right? It had the 1 red one, and so we added 7 other dots on there, so it has 8, right? In order for this to happen, it has to steal those 7 electrons away from another atom, and that's impossible, right? There's just not enough energy for that to happen. And so this is not how lithium is going to become stable. It can't just add on all of the remaining electrons. It would take too much energy from itself. And so we have to think about what other options this lithium has. So let's try and go in the other direction. So if we lost the 1 electron, right, that's way easier than trying to steal 7 from someone. Think of it. Is it easier to rob 7 banks or just give someone 100 or give someone like $1? Right? It's way easier to give something away than it is to take from multiple people. And so when lithium gives away that 1 electron from that second ring, its new outer layer, right, the last ring that has dots on it, is the first one. We know that the first ring only needs 2 dots, 2 electrons, and so now it's full. And so now this lithium is stable. There are more protons, there's 3 in the middle, than there are electrons, 2 on the outside, and so this lithium is going to have a charge. The charge would be 1 plus because there's 1 more proton, positive charges, than there are electrons, negative charges. And once again, to find the charge, we would take the number of protons and subtract it from the electrons. 3 minus 2 is 1. And so this rule of having 8 or filling the last shell is called the octet rule. Okay? The octet rule has 2 parts to it. The first one is that atoms are more stable when they have an octet of valence electrons. What that means is that they have 8 valence electrons, right? OCT, that abbreviation, like octopus, or what's that? Octagon, like in UFC, or the octagon, the shape itself, right? All of these have either 8 sides, 8 tentacles, right? And so oct means 8. In this case, we're just talking about 8 valence electrons. The second part of the octet rule is that atoms are going to react to have the same number of electrons as the closest noble gas on the periodic table. And by closest, we mean closest in atomic number. And so the noble gases are the elements in the very last column on the periodic table. Okay? So, before we talked about how, like nitrogen is going to take some electrons because it can, but lithium can't, right? And we said before it's because it was too much energy. And that's true for most metals. Most metals are going to have less than 5 valence electrons, and so they need to steal a whole bunch. And so what metals are going to do is they're going to lose all of their valence electrons. The reason is, just like with this lithium, when they lose their valence electrons, they're uncovering a new layer underneath that will always be full. Right? We always have to fill the layers closest to the nucleus first, and then we spread out, and then we spread out. So if we get rid of whatever that last layer is, the one underneath of it has to be full because we couldn't have moved on to the next one without that happening. And so that's why metals will always lose their valence electrons, because it's easier to give things away, and they will always have something full underneath of it. Non-metals are typically going to only need to gain like 3 or 2 or 1 electrons. And so rather than giving away a whole bunch, they can just take a couple. And so non-metals will always gain electrons until their valence shells are full. And once again, most times they're going to be gaining 2 or 3 electrons. Not very much in the long run. And so that is the end of the guided notes. Okay? You have everything you need now in order to answer the reflection questions. But once again, before you get to that, you're going to work on your customizing your periodic table. These instructions don't really need too much explanation from me. I'll still walk through them, but you should be able to click through these slides on your own in order to add the right thing. So let's start. You should have your periodic table, and we're going to add a bunch of colors to it. So first, we're going to make super clear where all of the non-metals are so that you know exactly which elements are always going to gain electrons, okay? And so as you can see on the screen, all of the non-metals are the ones that are highlighted in yellow. The only non-metals that are not highlighted in yellow are column 18. Okay? Anything that is not in yellow or later blue, you can count as a metal. Okay, so far, everything that's on the periodic table besides this little yellow area right here is going to be a metal. There are different types of metals. One that we're going to focus on specifically are the transition metals. You're going to highlight those in pink, and so that's this section here in the middle. Okay, we're highlighting this section because it's kind of like a rule breaker, and so we just want to have a visual so that when we realize we have an element that's in this spot, we're going to have to think about it just a little bit differently. I know what's going on back there. Okay, so we now need to show what elements are not going to react. They're not going to bond with anything. Okay, those are going to be the noble gases in column 18, right? The octet rule says that every element is going to try and resemble the closest noble gas when they get 8. And so if every atom is trying to look like the noble gas, then that means that the noble gases must already have a full outer shell. And so that column 18, sorry. Okay. So all of these elements that are in blue on the right here, they all have a full octet and will never participate in bonding or reactions. Okay. So let's look at some metals from group 1/column 1, right? So we learned that the columns on the periodic table is the ones that go up and down are also known as groups. And so group 1 is the one on the far left that has hydrogen and lithium and sodium in it. And so those are the Bohr models that you have here. Hydrogen is the 1 plus, lithium is the 3 plus, and sodium is the 11 plus. And so what I want to know is, what do you notice about these Bohr models, right? You're not taking any notes. We're just kind of trying to figure out what or why this next thing is true. Sorry, emails. And so what I'm really getting at is, other than the number of protons being different, like, what do you notice? And also, other than the rings increasing, yes, that does happen, but what else do you notice about these Bohr models? Think about what's the same about them, right? Number of protons being different, the rings increasing, those are all different things. I want to know what is the same. And so hopefully what you noticed was they all have the same number of electrons on the valence energy level, right? Hydrogen has 1 on the last ring. Lithium has 1 on the last ring. Sodium has 1 on the last ring. And so all of these elements that are in group or column 1 all have 1 electron. And this shouldn't be new because we've talked about this with Bohr models. But every element that is in the same column on the periodic table shares the same number of valence electrons. Every element in column 1 has 1 valence electron. Every element in group 2 has 2 valence electrons. And so we're going to add those numbers to our periodic table so that we can always have something to check exactly how many valence electrons these elements are going to have. So above each column on your periodic table, there is a blue number, right? And that's trying to tell you the column number. What we're going to do is we're going to make it so that these column numbers are true to the rule so that we don't have to kind of do any extra thinking. We can just check to figure out what the number of valence electrons are. So the section that we highlighted in pink, these transition metals that make up the middle, they, like I said, are rule breakers, and they're going to mess up the rule that I'm trying to explain to you. Okay, and so what we're going to do is we're going to get rid of the numbers above it. So using a black Sharpie or your pencil, or I guess whatever color you want, you're going to get rid of those numbers. So from 3 to 12 up at the top, you're just going to black it out. Okay. The reason is SC does not have 3 valence electrons. V does not have 5 valence electrons. And so it interferes with that rule, and I don't want you guys to get confused. I want you to have a way to easily check and reference these ideas. So what we're going to do is, if we sat down and we drew the Bohr model for boron, carbon, nitrogen, oxygen, fluorine, helium, we would see that the numbers above those columns do not match either. Boron does not have 13 valence electrons, and so we're going to change it. And so what we're going to do is, for columns 3 to 18, we're going to rewrite the column number. So instead of 13, it's 13A. 14 is 4A. 15 is 5A. 16 is 6A. 17, 7A. 18 is 8A, right? And so once you've written them all down, you're going to cover it in black so that you don't see it anymore, and all you see is your new versions. Okay? We're going to do the same thing for the first 2 columns as well, just so that all of our, column numbers match. And so instead of 1, we're just going to put 1A. Instead of 2, we're going to put 2A, and then cover them in black. So now all of our column numbers have a number and a letter, so that we can always look back and, oh yeah, everything in 1A has 1 valence electron. So now you're going to flip your periodic table over. Okay. We are going to add information to the back that relates to the column, just so we're not kind of cluttering the front. Each group is going to have a different charge when they become an ion, right? Because it's all based on the number of valence electrons, every single element in a column is going to have the same charge, and we're just going to write them down on the back. So group 1A has 1 plus, 2A has 2 plus, 3A has 3 plus, and that is it for the pluses. 4A you're going to skip, and I'll explain why in a second. 5A is 3 negative. 6A is 2 negative. 7A is 1 negative. And 8A you're going to skip, but they also don't apply. Okay? And so 4A was skipped because they don't form ions often, right? Do they have the capability to? Yes. Are they ever going to do that for us? No. That is a much more complicated and expert level chemistry idea that we are not going to concern ourselves with. The reason why 8A was skipped is because at no point in chemistry will they ever form an ion. It is impossible for them. Okay, so with that, your periodic table should be complete, and you now have everything you need to complete a reflection. I hope you guys have a wonderful day, and I will see you guys on Monday or Tuesday if you're in my 1st and 7th period.